principles of software engineering. We are discussing design and implementation. This will be our last chapter for the semester. So the topics covered: design choices, design patterns. Just brief actually about the design patterns. We will explain or actually address or discuss one design pattern, the observer. I will speak about design problems, implementation issues, and software reuse in general. All right, design and implementation. It's one of the stages that we have in software development. Design and implementation itself is actually composed of two steps: design by itself and implementation. However, they are usually mentioned together as interleaved process because design is usually attached to the implementation. And the main or the essential differences: the first one is visualizing what we are going to create as a code. So the design itself is having a view on what we are going to code, creating its own design, building its block, and setting up the communications or the interfacing and the relations between the components, then transferring that view into an executable file using implementation. Implementation means realizing a design that I put, a view that I put about a component of a software, some components, then I transfer them or translate my design into instructions or into program that can be converted to an executable file, or a file that we can use as an executable source of a program or a software. So this is the idea of design and implementation: creating the components in an abstract view as design, then implementing them by coding or creating codes for them or programs for them. All right, buy or build. Before we go through the design and implementation, we should actually ask this question: should I buy a system if it is available, or build it from scratch? Well, if it is available and it can fit you, you can buy it. If the price is affordable, you don't have to create everything from scratch. There are many applications that can be configured to fit to a good extent actually to our own purpose. And we explain about the commercial off-the-shelf systems, the COTS. These COTS can be configured. We have like general category that fits. Maybe some categories fit medical applications, some categories fit education, others fit like maybe online shopping, and so on. So these can be configured to fit the purpose of the client. So if we can configure them and adapt them to our own need, why do we need to buy them? Why do we need to build them from scratch? You don't have to do that unless the requirements are difficult to compromise. You cannot give up the requirements. That means most of the requirements are essential and they cannot get a match from codes to them. Plus, stability itself is a major issue. Why? Codes, if we configure a lot of things in codes, we wouldn't be able to expect the best stability in the system, because once we apply our own configuration, the stability will be compromised and we will have to deal with a lot of faults, failures, and so on. All right, design patterns. Now, software development is not a new discipline. It's been available for quite some time, since 60s. But the popular form of it started around 90s. That means you can say around 30 years. That is exactly when a concept of reuse came to existence. We will speak about reuse in a while. But what it means industry became extremely popular, especially for internet-based, like things related to web-based applications, shopping, industry, education. All these things required some solutions for available problems. And these problems were addressed by specialists, developers, and professionals in the field and they came up with good solutions, good practices for design, and they called them design patterns. So a common problem, and this problem can be categorized in many cases or can be found in frequently available cases that we have in our reality. This problem is solved by a certain design, and this design is effective, it's been tested, and its outcome is acceptable, and there is no problem with this available solution. So they created a template for this solution. They called it a design pattern. So it's an abstract knowledge. Abstract why? We give you the way you solve, the way you create your own solution, but we don't give you the design itself or the concrete solution itself. We just let you have the abstract knowledge, and then you will do your own part so that you customize your solution based on your own instance of the problem, because problems may not match 100%, but to a very good extent they match. Usually we have design patterns a lot in object-oriented because they have relevant characteristics like inheritance and polymorphism. So what are these design patterns? Design patterns actually and pattern languages are ways to describe best practices. Let me read the definition and I'll explain about these in details. Good designs and capture experience in the way that's possible for others to reuse the experience. Now, I said in software we have up until now we have come across thousands of problems, and these problems more or less they match in their description to a very good extent. So in that case, how about if a solution is formulated? Okay, so a good practice for solving this problem is being given as a design pattern. So yes, that's actually a good scenario, and this is what we call design pattern. We have a solved problem. So we have an experience of someone who solved the problem, and seems the solution fits very well the description of the problem, and it can be reused, reapplied for new emergent problems that match the description of our problem. So this is exactly the pattern that we use, or we say here in this case design pattern. We spoke about architectural patterns because they were about architecture or relevant to architecture. Now we speak about design over architecture, so the topic is related to design more than architecture in this case. Okay, what do we have when we explain about the design pattern? First of all, we have the name. A name that makes sense, that means gives you the idea of what this design pattern is all about. A general problem description, description of the solution, and the solution usually we don't give you the design, the whole way of writing or coding, no, or a whole way of designing your own system. No, we give you just a template to create your own instance of the solution. So that's what gives you the design pattern. The consequences, well, how about when we apply this solution or this design pattern to solve some problem, what about the advantages and disadvantages? What about the consequences? I mean the trade-offs, the compromises that we need to have. So these are usually the general elements that we have in a design pattern. Now we have a very popular example, which is the observer. The observer, as the name says, actually it observes a state of an object. If the state is changed, then we may display based on a new state. So that is here where comes the description. So we have a different display that is separated from the object itself. So we have an object and its state. So we have two separate, you can say, objects, object and its state. and then we can display based on the state of the object. If it is changed, we have a new display type. What kind of a problem it is solving, or why do we need to address it? If we need to display in multiple ways or different states of the same object, or if the future is not exactly known about what to be displayed in later on, and now we have, let's say, 5 or 4 or maybe 2 or 3 or 10 types of display representation of an object, but we say maybe we will have other types of representation in future, so we keep a margin for having new observers of the same object with different state. The description of the solution, we will have it in UML in a while. The consequences also in a while, not now. Let me just explain about the solution. Now look, we have our own subject as an abstract class, and we have observer also abstract class. It has the functionalities that we need for the subject, the general functionalities, attributes, and so on. And here we have also the general mechanism for update the presentation. And then we have 2 concrete classes. The first one is concrete object. The first object is concrete subject that inherits the functionality and the attributes of subject, and it does what? It represents the state of the subject. And at the same time, this concrete subject actually is returning the state subject and passing it to what? To a concrete observer. So the concrete observer is an object that inherits observer itself, and it has a direct relation with the concrete subject, where it communicates to get the update of the state of the subject here. So now our subject, the abstract class, has as many observers as needed. How many displays do you want? This is just a simple example. Display is one of the applications we have. We may have other representation other than display. Okay, so let's say we have 5. So we need to have 5 observers in that case, and the state will change 5 times and will notify the concrete observer, and the concrete observer will update to 5 observers to display the state. That's exactly what is written here, but in more details. So the description, we have different displays for the same object, but with different states. The problem, we need to isolate the state of the object from the object itself. So we may have different types of representation. Let's say maybe graphical, maybe tabular, maybe different types of graphical, and so on. So we isolate the state of the object from the object itself, and we represent it using concrete subject and concrete observer to update the observer. All right, the consequences. So we spoke about how the solution is made through all these 4 objects, 2 abstract and 2 concrete, and we have these methods that update actually the mechanisms. The consequences, now look, let me explain here. The subject has no direct relationship to what it updates it. Concrete observer is updating actually the state of, not updating the subject, what it updates its representation. So we don't have exactly direct relationship. We reduce the coupling problem. So there is no exact coupling problem here. However, enhancing the way that we can communicate between subject and concrete observer is a bit tough. So enhancing the way we can do this mechanism is not easy. This is one of the problems, optimization. So the performance may have problems. One more thing, since we have this kind of a bit long communication process, we may end up with having like some unnecessary or extra processes that we need to do. Usually these are not preferred. However, this is extremely practical in many applications. One of them is this. Look at the subject. We have the subject state is like display of some maybe levels based on A, B, C. So A certain level, B another level, C another level, etc. We need one with bar diagram and another one with pie diagram. So these are statistical outputs for representation. You may create an observer to represent in bar diagram and another observer to present in pie for the same subject. So we are isolating the state of the representation here from the subject itself. All right, design problems. Now we said about the common practice of design patterns. How can we apply them? Usually in our reality we have problems that match the best description of some design patterns. So these design patterns are already available. They solve some certain problem. If our problem is matching one of those, then we can use it. How to know? How can we know what is the best match when we use? Actually, design patterns themselves are taught as a separate subject, as a separate course, usually in postgraduate. However, you will study them in some other courses like software quality, like software design, not this principles of software engineering. This is too elementary to teach you the details of design patterns. However, we can give some idea. Now, we explained about when we need to isolate the state of an object from the object itself. We can use observer. This is a common practical problem that we have while designing a software or developing a software. Sometimes we create a software from an incremental process or using an incremental process. And due to that, we may stack objects on top of each other, like a number of objects, and the view of the output view of all these objects may not seem nice. So we would be interested in interfacing these objects with a nicer design that actually shows us the real outside world. In that case, we can use what we call facade pattern, design pattern. In this facade design pattern, it's pronounced facade. Okay, this one is pronounced facade. Actually, it provides you a nice view, a nice interface to cover actually all your hidden objects or all your internal objects from being seen by the outside world, especially if you have like stacking of incremental process where you don't want your objects to be seen in that maybe unorganized manner. Sometimes we may think about a way to access to some elements in a collection. So we have a collection of elements, we need to access some of the elements. However, we are not interested to know how these elements or how the collection is being implemented or was implemented. So if we are interested in such thing, we can use iterator pattern. And this is extremely popular with Photoshop applications. Is very popular, accessing some elements in collection. Think about pixels, for example. Sometimes we need to extend the functionality of a class or an object even of a class during the runtime while we are executing a program. We need to extend the functionality for a certain reason. If you want to do that, you can use decorator pattern that will do this extending functionality process for you. Implementation issues. So we said about the implementation, transferring a design that we have into executable program through programming, so writing codes in programming language. But this is not usually the main concern that we have, although it's one of the concerns or issues that we have. Writing codes needs actually experience. It's not just straightforward the way people may think. However, that is not adequate. We need to think about the concept of reuse. If the component or the element or a system or a subsystem is available, do you need to create it again? This is a big question in software. So if it's available and fits your design, no, reuse it. Or if you want to design, why do you need to come up with your design which may not be efficient and you will waste your time and effort? While a design is already available, how about reusing the design? So this is an issue in implementation, the reuse. And we will see the levels of reuse in a while. Configuration management. Now, we mentioned about implementation itself is transferring some design components into written codes that can execute. So we're creating components. We need to have certain management in terms of managing their interfacing, managing their communication with one another to create the whole system or to compose the whole system. So this is what we call configuration management while implementing. Host target development. Now, if you are a software developer, you will develop your software using your own computing ability or facility. Maybe one computer or two or three, or maybe a large computing facility with maybe parallel computing. However, this is not usually the computer that a client will install the software to use it with. So your computing ability or machine or the computer that you use to create a software usually is called in this case host, which is actually is called this in this case host, not usually. It is host in this case, but usually it has its own design and customization. You may have different software packages installed. You may have higher performance in that machine, etc. So there may be a lot of things in the environment that you design or develop with not available in the target system. So the client will take the software, install it in his own system or her own system. This is what we call target. This target may not have the packages of the software that you have or the capabilities that you have. So that's what we call host target development problem. We usually have this kind of mismatch in design. Reuse. So early days of software development were tough. Everything was created from scratch, and structured programming was the major actually or the common process in programming, because object-oriented came a bit late after that. The idea of having everything from scratch is not exactly practical, especially with having a lot of things that can be reused. So the only reuse maybe available that back then was reusing some functions or reusing templates or reusing objects at max. So just calling some class or library of classes and receiving some objects or templates from them, or maybe some ready functions people designed or methods that you can reuse. However, this was not adequate when the boom of internet came, and at that time things started taking a new direction, especially like web became available and commercial stuff became internet based. So web applications became extremely popular and the demand for software became very rapid. So that rapid increase of demand for software has made the software design and development oriented in a reuse fashion. So reuse itself became like, well, why do we need to create everything from scratch? Well, we have most of these components that we can just adapt. They're already created. We can just adapt them, configure them, and fit them together and create the rest of the software that we cannot create it from reused components. And that was the idea. It saved time and effort for sure. What kind of reuse levels do we have? The first one is the abstraction level. We don't exactly use codes in this case. We use a way to create codes. So we are using here in this case knowledge. So we reuse knowledge. So the knowledge is being reused in this case and not any other thing. Object is very similar to when you write codes in Java or Python or C, C# or whatever. C has no exactly objects, rather it has templates. But in object-oriented, you can import some maybe package or import some class and use its objects for writing codes. That's reuse, because you are not creating that object, it's created, just you are just using it. A component, well, we use components, we reuse actually components, or we are using them every day in a reused fashion from other software. Think about text editors in emails. Think about sometimes you want to calculate something, you press for calculate, it takes you to the calculator. So the calculator is not designed, it's borrowed, in this case reused. There are many other text editor we said about it, maybe other functionalities like photo, if you want to view a photo or something, and in that case you are reusing a whole component, not just an object. You may reuse a whole system like codes. You just take the whole system and configure it and use the entire application as a reused system. You just need to configure it and maybe apply your touch to it to adapt it to the system or to the desired system. Now here in this case we may have some stability problems, so you need to think about it. This is the mechanism of our reuse. We have the abstraction level for either architectural and design patterns. Both of them can be reused. We spoke about both of them. We may reuse whole systems like codes. We may use like components, framework. We explain about them. Available components. Maybe calculator is one of them. Maybe calendar. Why do you need to design a whole calendar if the calendar program itself is available? You can just reuse it. And object, and these are the smallest in this case that can be reused. All right, what is the cost of reuse? You say reuse, it's already available. What will I pay for it? You may not pay in cash and money. You may pay in your time to find the best match to reuse it. And you may pay time and effort to adapt it to your system. So it may not match 100%, so you need to adapt it to your system, especially if it is like codes. You need to adapt it, configure it, so it needs time and effort. Plus, you may need to pay for it. If codes, not all of them are free, so it depends on their license. So some of them are paid, so you need to pay for them. They're commercial. And these commercial software packages or applications, you have to pay for them to use them. So these are the different costs of using or reusing software components. The time that you need to spend to reach them or to find them, the time you need to spend and the effort, the knowledge to adapt them, configure them, or maybe the payment you need to make to be entitled to use them. This is the end of the chapter. And this is the end of all theory topics that we are supposed to cover in this semester. I hope you guys will benefit from these videos, and I hope you will also achieve great results in your assignments and in the final exam to come. I will just upload some practical videos, as I explained, maybe around 8 tomorrow or the day after tomorrow. But before that, I'll upload an assignment, the last assignment, and its submission will be on 22. You will get a notification from your system about the assignment. And the best of luck in your next stages to come. Goodbye.